Oh, yeah. Sorry, I forgot to unplug this. Okay. All right. So are there any questions before we get started? We're going to keep working our way through 7 for about an hour. We'll try to stop about 10 to do some stuff with the review for the exam. But are there any questions before we get started so far with what we've done in the substitution reaction chapter? If you look at the study guide for exam 2, it has information about chapter 7. Chapter 7 is not tested today. When Dr. Barrios Sosa and I loaded that, neither one of us remembered to check what the study guide was showing. All right, so if there aren't any questions, we'll just get back into 7.8. So in 7.8, what we've already done is we have these 2 reactions, 2 different types of substitution. Oops, can't see that, sorry. Okay, so you had substituent or substrate, excuse me, with a leaving group, and then you have your nucleophile. And then what you end up forming in some solvent is your product that now contains the nucleophile, and then your leaving group is gone. Okay, now the leaving group is going to end up, we always just say, in the trash, which is literally exactly where it goes. Usually the way these reactions end up is you get 2 sets of solvents. You have the solvent that contains your product, and you have a solvent that contains the leaving group. And the solvent that contains the leaving group, unless it is toxic, is literally just poured down the drain. It's usually water and some salt. So what we have already done is we have looked at our substrates, and we've determined which mechanisms are possible depending on whether you have a methyl, a primary, a secondary, a tertiary. And they differ in whether they'll operate or participate in SN1 or SN2 reactions. Let me make sure everybody is muted. Oops, that's not where I need to go. If you know you're not muted, there we go, here's one. Okay, nope, that's everybody. Okay, so when you have SN1, this is a 2-step reaction, so you have to make a carbocation. So the tertiaries will always go through that mechanism. The secondaries will as well, but you have to use some caution. Methyl and primary will not. For SN2, you need backside attacks, you need to have open substrates. Methyl and primary will work. Tertiary or secondary might work depending on other circumstances. Tertiary won't work at all. So that's kind of where we are right now. There are a couple other substrates that we discussed, and those are on the last slides. Let me get this chat real quick. Oh, Nick. Oh, okay. All right, so now what we're going to do is we are going to talk firstly about the nucleophile, okay? So there are 2 types of nucleophile. There are nucleophiles that only have lone pairs of electrons. So these are neutral with lone pairs. And the other type of nucleophile is negative with lone pairs. And so in order to discuss these, what we're going to do is we're just going to make a couple quick comparisons between SN2 and SN1 reactions. Okay, so again, SN2 reactions, these are one step. Okay, and the rate of those reactions is equal to a rate constant times the concentration of the substrate that has the leaving group times the concentration of your nucleophile. Now I want you to put a negatively charged nucleophile in your rate law for SN2. Okay. So by looking at the rate law, you can tell that the concentration of the nucleophile directly impacts the rate. So the rate depends on the concentration, moles per liter concentration, or the amount of the nucleophile. If you want your reaction to proceed faster, you just add in more nucleophile. Okay. If you want to make it, you can also increase the rate by increasing the substrate concentration, but right now we're just focusing on the nucleophile. Okay. The other thing that we have to consider from our first statement is that this is a one-step reaction. Okay. It's one step, but it's bimolecular. So when you have two species in your rate law, that's called bimolecular. One step and bimolecular requires a collision. Okay. The two species, the substrate and the nucleophile, have to physically collide in space or in the solvent in order for this reaction to take place. Okay. In our one-step reaction, if we look at our substrate, and this is just a methyl substrate just because we know it's going to work. This carbon is partially positive. Okay. It is in a polar bond and it is slightly electron deficient, but it's not as electron deficient as a carbocation. Okay. So when you are trying to attack a partially positive carbon, you need a stronger or a strong nucleophile. And strong nucleophiles are characterized by having a lone pair and a charge. Okay. So when you see, there are a few exceptions, and I'll talk about those in a few minutes. There are a few exceptions where you can have a strong nucleophile that doesn't carry a charge. Okay, but most carry the negative charge. And just write a little note here, exception are sulfur nucleophiles. Okay. And we'll get to that again in a minute. So if, when you're looking at your reaction, you see a nucleophile here with a negative charge, that is going to lean your analysis towards picking the SN2 mechanism. Okay. Now, if there aren't any questions, I'm going to erase this bottom part about the SN2 and do a similar set of notes about SN1. Okay. All right, so the SN1 reaction is two steps that has a rate law where the rate of the reaction is equal to a rate constant times the concentration of the substrate with the leaving group. Okay. So the rate law does not contain the nucleophile. So the nucleophile is not or does not participate hard in the slow step. So SN1 reactions will have a rate that's independent of the concentration of your nucleophile. You can put as much nucleophile in as you want, but that will not affect the rate of the reaction. The rate of the reaction depends only on how fast the leaving group leaves. Okay. And if you remember, how fast the leaving group leaves is related to the stability of the resulting carbocation. So if we write a little brief reaction, now we have our tertiary substrate as a tertiary alkyl halide. The slow step is in forming a fully positive carbocation. A fully positive carbocation is more electron deficient than a partially positive carbon that's required in the SN2 reaction. So this is very electron deficient and needs electrons very, very badly. So your nucleophile requirement is simply that you have a lone pair of electrons. Okay? So what we say is weak nucleophiles are preferred for SN1. Now, one thing you might be asking is, or thinking is, am I allowed to, will it be okay if I use a strong nucleophile in SN1? Yes, but you don't have to. Okay? You have to use a strong nucleophile for SN2. SN1, you don't need to. So when you consider the SN1 reaction, I want you to think about what you would do if you had a fly, a house fly, buzzing around your home and it's driving you crazy. And you go to your closet that has your fly killing apparatuses, and you have a choice. You can either choose to kill that fly with a fly swatter, or you can choose to kill that fly with a bazooka. Okay. A weak nucleophile is like a fly swatter. So a fly swatter is a weak enough tool to create the product at this point. You can blast this thing with a nucleophile, with a bazooka, but it's going to make the reaction much harsher in conditions. Okay? If you use a bazooka in your house, you're going to need far more than a paper towel to clean up the mess. Okay? You're going to need a contractor. So when you pick your nucleophile, it's always dependent on what type of carbon you are attacking. A partially positive carbon or a fully positive carbon. Okay, so when you say what your weak nucleophile is, it's a species that has, can be neutral, but has to have that lone pair of electrons. So let's make a list of various types of nucleophiles, unless there are any questions before we move on into that section. Okay. All right. So there is a list of some common nucleophiles. Okay. And we're going to classify them as strong and then weak. So in the strong, you're going to have the halides, iodine, bromide, and chloride. Okay. Now these aren't equally strong, this is strength increases in this direction for the halides. Okay, now the reason that is based on what is called polarizability. Right? And polarizability is the ability of a solvent to distort the electron cloud. Okay. So chloride is smaller than bromide, which is smaller than iodide. Iodide is the largest halide and has a lot of electrons. It's big and it's fat and it's squishy. Okay, it's like a comfortable feather pillow on your bed. Okay, and why people like feather pillows is they can push on them into making them into a shape that they like. So pushing and shifting the feathers within a feather pillow is the same idea as polarizability. The solvent is going to smush that electron cloud so that these, this is a more negative, just by electron distribution, nucleophile. So that just makes it a stronger nucleophile. They'll all work, but of the three that are listed here, iodide is the best. Now, fluoride, which is also a halide, is over here in the weak, okay? But I want you to put a star in it because I'm not going to ever use fluoride because fluoride chemistry is not particularly easy because fluoride is biologically a monster. The problem with fluoride and why you put it over here is its ability to function is solvent dependent, much more so than any of the other nucleophiles. So the other members of the strong group would be hydroxide, okay, and then what we're going to call RO. So let me erase this. RO is essentially what you get when you take a salt, an ionic salt. Again, you always ignore the cation, and what you end up with, this would be called methoxide. You could use ethoxide. You could just have a carbon chain here. It could be branched like tertiary butoxide. They look like deprotonated alcohols. They're the conjugate base of deprotonated alcohols, but you can't use an alcohol to generate this species. You have to use a salt. So R is just some hydrocarbon chain attached to a negatively charged oxygen. But what I want you to put a little box around these two. Okay, and then down here, I want you to write, these are strong bases, okay? And that's important because when we get into chapter 8, we're going to see something similar to this, but we're going to be using these a lot more, but we're going to use them as bases, not as nucleophiles. But just have that in the back of your mind that they're strong nucleophiles, but they're also strong bases. The other strong nucleophile that you've seen, we've talked about this one a little bit in the past, is nitrile. And then the last group are the sulfur-containing groups, and there is thiol, which is strong, so it's sulfur with a negative charge. But because sulfur is polarizable, just like the halides where you can smush the electron cloud, neutral sulfur species also are strong nucleophiles. The other is to replace one of these hydrogens with a hydrocarbon, so RHS. Weak nucleophiles are going to be things like water. You could use an alcohol just anything that's going to have a lone pair without it, but with a neutral charge. Okay, are there any questions about the nucleophiles before we look at leaving groups? Okay, so the leaving group. Okay, so the identity of the leaving group is important in both cases, in both SN1 and SN2. Because if you have a leaving group that won't leave, neither reaction is possible. Okay. SN1 reactions are a little bit more sensitive to the identity of the leaving group. And that's because the loss of the leaving group is in the rate determining step. Okay, so that is the formation of the carbocation is the slow step in this reaction. So SN1s are more sensitive to the identity of the leaving group. But if you have a bad leaving group, neither reaction will proceed. Okay. Okay. So what makes something a good leaving group versus a bad leaving group? So a good leaving group is going to be the conjugate base of a strong acid. Okay. So for example, if we take a tertiary alkyl halide and we put iodine on there, this is a tertiary substrate, so we have to make our carbocation intermediate, and so we'd make a tertiary carbocation and we would release iodine. Okay. Now there's no Bronsted-Lowry acid and base reaction going on here, okay? But your thought process should be that iodide is related to hydroiodic acid. Hydroiodic acid is strong, which means it fully dissociates and creates a lot of very stable iodide anions. So since this is a stable conjugate base, it's easy to leave as a leaving group. Now if we take the same substrate or similar substrate, a bad leaving group is going to be the conjugate base of a weak acid. Okay, so let's say now we have our tertiary alkyl halide, or sorry, our tertiary alcohol. So we have an OH group here. So since this is tertiary, it has to go by SN1. So you'd say, well, hydroxide would leave, make a tertiary carbocation, release hydroxide. But in your thought experiment, hydroxide is related to water, and water is a weak acid, which means the equilibrium dominated species is water, and you get very little hydroxide, which means this is a more unstable species. If this is unstable, it means this reaction won't proceed. Okay. I'm going to erase some of this stuff at the top. Okay. But you're not stuck. So there are, you can convert a bad leaving group into a good leaving group. Okay. Right. And we're going to split how we discuss this into two groups. Okay. If your substrate is methyl or primary alcohol, so these are going to be the types of leaving groups you're going to have to know how to fix. You're going to fix with something called tosyl chloride. Okay. If you have a tertiary alcohol, and we're going to, like I said, ignore the secondaries, you're going to fix that with a strong acid. I didn't mean to erase so much of this. Are there any questions about this idea before we look at fixing the leaving groups?
I do have a question.
Sure.
So when you were talking about the stable and unstable, could you like go over quickly one more time how like you know one is stable or unstable?
Sure. Do you mind if I erase some of this to write it out?
Yeah.
You do mind or you don't mind?
It's all right, you can.
Okay. All right. Okay, so the reaction, we'll split it up into two things. So the reaction that we're trying to do is going to be some kind of, a SN1 substitution. And what we're trying to do is just replace the iodide with the chloride, okay? But what we have to figure out, though, is what happens in the slowest step, which in this case is the loss of this leaving group, okay? So what we would say is, if the iodide leaves, then we form a tertiary alkyl halide, which would get automatically attacked quickly by this strong nucleophile. But we also have iodide in the reaction, okay? So if you're going to say, how do I know that iodide is a good leaving group? Okay, so then what you're going to do is you're going to think about the iodide acid-base reaction. Okay, so it's not actually happening, it's just something that you have to think about. Okay. So this conjugate acid of iodide is hydroiodic acid. And you would say hydroiodic acid would participate in this reaction. Okay. Hydroiodic acid is one of the 7 strong acids, which means the forward reaction is the only reaction that takes place. This has a gigantic equilibrium constant K, and it has a pKa that's negative, which means it's a forward-driven process. If it's a forward-driven process, it means that the iodide is a stable anion. If it's stable in this condition, it's stable in this condition. If this is stable, then the forward reaction here is likely to occur. Now, I draw these as forward. There is a chance that if this is close to this, if the iodide is closer to the carbocation than the chloride, it'll go back. But we are always considering making a new product. But the ability of the leaving group to leave depends on the equilibrium in its corresponding acid-base reaction. Does that make sense, Jay?
Yeah, thank you.
Okay. Are there any other questions about about that. Okay, there is a table in your book that has just kind of this idea with good leaving groups versus bad leaving groups. I'm not going to pull it up just because the examples I want to use I'm going to show you, but I will find the table and so you can find it in your book. Okay, it's on page 323. Has a table of good leaving groups and bad leaving groups. Good. Okay. Now, on the next page of your book, page 324, you get a table showing you the most common leaving groups. I will show you how to fix the bad ones in just a minute. Okay. So the most common leaving groups. Okay. And they're in two classes. The first are the halides. And the ones that are halides that are related to strong acids are iodide, bromide, and chloride. Okay. The second group are called the sulfonates. Okay. And there's 3 listed, but the one we're going to work on is, so let me list them by name. So they're called tosylate, mesylate, and triflate. But the one I want you to be comfortable working with is the tosylate. So the tosylate leaving group is pretty big. So it has a methyl attached to an aromatic ring that's attached to the sulfonate group. Now, don't panic about the number of electrons around the sulfur. The sulfur, remember, is a group, or excuse me, period 3 atom, and period 3 atoms can expand their octet. So this is perfectly acceptable for a sulfur atom. Okay. So the source of tosylate is a compound called tosyl chloride, and it's generally going to be written TSCl. When you use the tosyl chloride to convert your leaving group, that's a separate reaction step that requires the solvent pyridine. So on a flashcard, you have to, or you should have tosyl chloride over the solvent pyridine. You don't have to know the structure of pyridine. I would recommend that you learn the structure of tosylate to be able to recognize it. Okay. So let me show you how that reaction would be written. And we're going to use tosyl chloride on, use on methyl or primary alcohols. So let's take a substrate, methanol. And what I'm going to do is I'm going to write the carbon in red, because we're always going to be attacking that red carbon in the substrate. Okay, so there's lots of carbons over in here. There's a carbon here, there's 6 in the ring. You don't attack any of those. You always are going to attack the substrate carbon. Okay, so your reaction step 1 would be the tosyl chloride in pyridine. Okay. And then what you make would look like this. There's the oxygen here, the sulfonate, your benzene ring, and your methyl. Okay. This whole thing is referred to as OTOS. That whole thing is the leaving group. The nucleophilic attack still occurs on the carbon in your substrate. So if I would have a bromide in my reaction, then the bromide will attack the carbon, and then this whole group leaves. And I would make my product, bromomethane, and then I would have OTOS that, in this case, I wouldn't put this down the drain because of the aromatic ring. That would have to go into organic waste. But that's how you would fix either a methyl, this is methanol, or if you had ethanol, it would work as well, as long as it's a methyl or a primary alcohol. Okay. All right, are there any questions on fixing bad leaving groups using tosylate? Okay, let's fix a bad leaving group on a tertiary substrate. Okay, so we're going to fix a hydroxide bad leaving group on a tertiary alcohol. Okay. So we're going to use terse-butanol. Okay. And we're going to treat it with a strong acid HCl. Now, because we're choosing to use HCl, the chloride is going to end up being the nucleophile. So if you wanted a bromine on here, you would use HBr. But this is good for right now. Okay, so the way that this works, because this OH group isn't going to leave as hydroxide, it won't break off this substrate. So the lone pair of the electrons on the oxygen go and grab the proton and release chloride. The substrate then looks like this, and then there's a chloride present. But I want you to think about what's happening at this oxygen atom. Oxygen is a pretty electronegative atom, but you're forcing it in this structure to carry a positive charge and make 3 bonds. So this oxygen atom is not very happy, and it's going to pull on electrons in these sigma bonds very hard. It can pull hard enough on these sigma bond electrons to break off and leave as a leaving group of water. Okay, so water is very stable, as you know. And then you would have your chloride. Actually, let me just write it like that because it's not negatively charged. Okay, then the chloride will attack in the nucleophilic attack reaction, and then you'll make this compound. And then, oh, you would still have water, like that. Okay. Are there questions about the leaving groups before we move into solvents? Okay. All right. Okay, so the last thing is the solvents. Okay, so we're going to have two different types, polar protic and polar aprotic. Okay. So in both cases, you can see that the requirement is that the solvent is polar. So down here, write a few notes. Non-polar solvents are not used in substitution reactions. At all. Okay. So the solvent has to be polar. Aprotic and aprotic. Okay. For a solvent to be considered protic, polar protic, it must have a hydrogen and a polar bond. Aprotic has to have any hydrogens, must be attached to carbons. So that way your hydrogens you can have hydrogens in polar aprotic. They just have to be in non-polar bonds. So the hydrogens have to be bonded to carbons. Okay. All right, so polar protic are always used in SN1. Polar aprotic are always used in SN2. So polar protic solvents that have hydrogens in polar bonds, that could be water. You have a hydrogen in a polar bond. You could use an acid. You could use an alcohol. You could use a bigger alcohol. You could use ammonia. As long as you have a hydrogen bonded to something more electronegative, those solvents will work. Okay. Now, what I also want you to think about is SN1, it's 2 steps. So you make a carbocation, and then you have a very electron deficient carbon, and you have these solvents that have lone pairs of electrons. So oftentimes in SN1, your solvent can be your nucleophile. Okay. So polar aprotic solvents, these have to have hydrogens in bonds to carbons. Just make sure I have. So the nice thing about the polar aprotic solvents is they're generally given like abbreviated names. Okay, so this is dimethyl sulfoxide. And we just call it DMSO. So sometimes DMSO is the only thing you would see written underneath the reaction arrow. Right. This solvent is called acetonitrile. ACN. Okay, this one. Dimethylformamide. DMF. And then the last one is actually really big. Oops. And it's like a hexamethyl phosphoramide. Ooh, hexamethyl phosphoamide. Oh, sorry, phosphoramide. HMPA. So you don't necessarily need to know the structure of these, but you should know the abbreviations. And if you see abbreviated names, I mean, it wouldn't be the worst thing in the world for you to learn the structures, but generally if the structure of is shown, it usually will have an abbreviated name next to it. But you can tell, like if you draw in here these methyls, those hydrogens are bonded to carbons. Hydrogen bonded to a carbon, so they're polar aprotic. Okay. All right. Are there any questions about the solvents before we talk about why you need polar protic or why you need polar aprotic? Okay, so oops, here it is. So we're going to start with the polar protic. And those are used in SN1. So what we're going to do is we're just going to draw an energy level diagram. These are two-step reactions, so formation of the carbocation and then nucleophilic attack. Two transition states and one intermediate. Okay. And just a quick okay. So in your SN1 reaction, you make cations and anions. Okay. In the step that forms this species. Okay. The role of the polar protic solvent is to stabilize all ions involved at the intermediate. Okay, you need stabilized carbocations and you need stabilized anions. Okay. So again, water is polar and protic, so you'd be able to stabilize both of these ions. Questions about this? Okay. In the polar aprotic, those are for SN2. Okay. Now SN2 reactions, remember, all we have to do is get our nucleophile into attack. Okay. So we need our nucleophile to be ignored by the solvent. If and when the nucleophile is ignored, it's a higher energy species and more likely to attack that partially positive carbon. Okay. So in your one-step reaction here, what you're trying to do is keep this activation energy low, so that step, that nucleophilic attack, will occur. So we want to keep this low by maintaining a higher energy nucleophile. So I would encourage you to look at table 7.1 in your text, and it is a nice comparison of mechanisms, energy diagrams, rate laws, substrate requirements, stereochemistry. It's a nice way. At this point moving forward, the more organized you keep your reactions, the easier it's going to be for you to use them and draw them and understand what's happening. So high organization skills work well at this point. Okay. All right. So how do you approach this? So we're going to spend the next couple minutes just looking at examples of how these types of things are addressed. So what we're going to do is we're going to say which mechanism, and this first one will be a little bit easier, which mechanism of substitution will occur. So I want you to have alkyl halide as your substrate, sodium iodide on top of the reaction arrow, acetonitrile on the bottom of the reaction arrow. Okay. So what substitution mechanism will occur, and then we'll draw the product. Okay. So the way that I want you to do this, even if you're like, oh, I automatically know, I want you to write substrate, leaving group, nucleophile, solvent. And then I want you to write SN2, SN1. And we're going to put check marks next to or underneath the mechanism that each one of these considerations will support. Okay. Now, the easiest one to consider first is your leaving group. So your leaving group is chloride. And chloride is a good leaving group. Good leaving groups are required for SN2 as well as SN1. Right. Let's look at our substrate. So we have a polar carbon here, so that would be the carbon that would be attacked. That carbon is attached to one other carbon, so it's a primary alkyl halide. Primary alkyl halides do not form carbocations. They participate in backside attack. That's an SN2 reaction. Now here you have a nucleophile hidden inside a salt. You get sodium cations and iodide anions. These are useless. I mean, they don't matter. They're there to get you iodide. Iodide is a strong nucleophile, and strong nucleophiles are used when you have to attack partially positive carbons that are in SN2 reactions. Acetonitrile is polar but aprotic. So now we have 4 checks for SN2, only 1 check for SN1. So the mechanism that will occur is SN2. Okay. And then you would, if you had to draw, you could draw a mechanism, and those are questions you should ask yourself. Can you draw the mechanism? Can you name, in this case, the reactant and the product? Now, one of the things that is common moving forward at this point is to bring back and keep working on IR and mass spec. So chloride is a 3-to-1 ratio in M to M+2. So if you hadn't been told it's a chloride, but instead just told it was a halide, with this mass spec information, then you could have identified that this is chloride. So you have to keep the mass spec and the IR in your mind, as well as all of the naming stuff. Okay, good. Okay, I'm going to give you, let's see, one more. I'm going to give you one to do on your own, and then we'll do one more together, and then we can start our review. Okay, same thing I want you to do that we did on the last one, but I want you to take this substrate in KCl and water. Okay, and I want you to determine which mechanism, SN2 or SN1, dominates. Okay, I'll be right back. Okay, does anybody need more time? Okay, so let's start. Substrate, leaving group, nucleophile, solvent. Okay, SN2, SN1. All right. Again, starting with the leaving group bromide, that's a good leaving group. Both SN2 and SN1 need good leaving groups. Okay. Substrate here, the carbon that is our focus is right here. That carbon is attached to 3 other carbons, so it's tertiary. Tertiary alkyl halides make excellent carbocations in 2-step reactions, SN1. Your nucleophile is in the salt. You can ignore the potassium. Chloride is a good nucleophile. It's a strong nucleophile, so it can be used in either SN1 or SN2. Water is polar and protic, SN1. All right, so let's see. Now it is 10 o'clock, so I want you to go down to your participants poll, and I want you to answer, do you want me, it's yes or no, do you want me to stop on 7 and start the review, or do you want one more problem for chapter 7? So yes means start the review. Okay. All right. Okay, so you can stop voting. It's clear. Nobody's voting no. Okay, so let me erase this. All right. Okay, so you tell me what you want to review. So the exam is, let me think about this. 3, 5, and 6. So that's acid base, stereochemistry, and then it's called like an intro to reactions.
I have a question.
Yes.
Can you talk about how resonance relates to carbocation rearrangement?
Sure. Okay, so it's going to take me a minute to think of a molecule. Okay. Okay, so this carbon is a secondary carbocation. And typically if you have a list, you could say primary will become secondary, secondary will become tertiary, primary will become tertiary. Okay. So based on this list, the carbocation, there won't be a hydride shift from over here because that would take a secondary to a primary. So you never go reverse, you never go worse. If you do a hydride shift over here, you stay secondary, but you could go secondary to secondary allylic because the ability to resonance stabilize the carbocation increases the stability of the structure. So if you can if you have resonance in your allylic carbocation, that will increase the stability versus just a regular non-resonance stabilized. So this one will shift here through a hydride shift to make this carbocation. This carbocation is allylic to this carbon here, which is vinylic. So, and this one would have a lot of resonance structures. So this would come over like that. And if you brought these back down, you'd end up back here. In it, well, sort of. It would look, the ring would be, you'd end up back here like that. So when you think about this, like this secondary carbocation has one structure contributing to stability. This doing the hydride shift makes this secondary carbocation, but it has 1, 2, 3, 4, 5 structures all contributing to stabilizing, and you have 7 carbons participating in the stability of those electrons. So that's why when you do either a methyl or a hydride shift, if it includes, if rearranging allows for resonance stability, it will happen. Now, you won't be put in a position of saying, well, what if I'm tertiary, but I could go to secondary allylic? Like, that's too hard of a thing to be analyzing right now. So the types of things that you would see, you could go secondary to tertiary, but allylic, tertiary to tertiary and allylic. Those are really the only types of things that I want you to be able to do. It wouldn't be like secondary allylic to tertiary, because I don't think that I don't think we have enough background to be able to do that.
Awesome, that helps a lot. Thank you.
Yeah. Anything else? No other questions, really?
I have a question.
Okay.
So this is number 7 off of the practice exam.
Okay, let me find that. Can you see my laptop now? My laptop screen? Or are you still
Yes.
seeing the whiteboard? Okay.
You're on Canvas?
Mm-hmm. So it's on the practice exam. Oh my gosh. Practice exam here?
Yeah, I think so.
Okay. What, 7?
Number 7.
Yeah.
So to find that, like, are we using pKa values to determine like pH and acidity, or are we looking at
you could use
like current hydrogen?
Yeah, you could use Aereo or pKa or a combination. So for example, you can say, and some of these things, like you have to use some things like to your advantage. Like if you look at these A, B, C, D, D is an alkane, which has a pKa approximately 50. Without a doubt, that is the weakest acid of all of the four. And if you look at the answer options, only one of them has D listed as the weakest acid. So you could be done with that question just by recognizing that of these four, the alkane is the weakest acid. Okay. But if you wanted to confirm, so this is a ketone. Ketones are about 20. Now A and B, let me see, A and B here, these are carboxylic acids, have a pKa about 5. But to distinguish these two, you would need area. So when you did the, here we go. All right. So A is atom identity. Charge will be on an oxygen. So in both A and B, here and here, when this proton leaves, the charge is on an oxygen. Okay. R is resonance. All right. Both of these will end up with a negative charge allylic to a pi bond. Negative charge allylic to a pi bond. So they both will have resonance here through the oxygen, carbon, oxygen, but then because of this pi bond, this has an additional component of resonance stability. So it's B, A, C, D. But really, this recognizing the alkane automatically answers the question.
So when we're looking at like the alkane versus like a carboxylic acid, so that is so we're looking at butane, but if we're like, are we supposed to be like adding those up? So like if we see a ketone there, like C looks like a ketone. So
it is a ketone, yeah.
Like, are we counting that twice? I mean, I don't know. Like, I was just like adding all those up, and it didn't. It just.
Maybe adding what up? No. So in here, not all protons are equally acidic. Hang on a second. Okay, so if you have butane, all of these hydrogens, for the most part, whether they're primary or secondary, they're all equally acidic. Okay, so all protons on this molecule have a pKa of about 50. But on the ketone, these black hydrogens are going to have a different pKa than the red hydrogens because of the proximity to the carbonyl. So these hydrogens in black, these are more acidic than these in red, because these would be considered alkyl, more like this, than adjacent to a carbonyl. So the pKa of a ketone saying that it's 20, it's talking about the more acidic protons.
Okay.
So you don't add up the pKa from this part and the pKa from this part. It's just the molecule itself has a pKa. And if you're ranking acid strength, you would want the most acidic proton.
Okay, that clarifies.
But you're not being asked to identify the most acidic proton. Not in these molecules. If you were asked the most acidic proton, like in B, you'd pick this one. even there's one hydrogen here and there's two hydrogens here. But because you're not going to get, if you had the hydrogen here, let me draw that. Where is it? I'm just going to make the bond really long so that it's not like right by that B. It's not really that long though in real life. Okay, so the loss of, if this proton as a leaving group would put a negative, would put anion negative charge on a vinylic carbon. So you're saying here, can you make a vinylic carbanion? No, you can't. So none of these three, the two that are here and the one here, are acidic. It's only this one here. There's absolutely no evidence of a vinylic carbanion. Does that answer your question?
Yes.
Okay, good.
Thank you.
Yep.
Dr. Walters, I have a question.
Yes, ma'am?
Number 20C.
Okay. Okay, so I need to look at the question. Oh, question. The following one-step reaction proceeds by oh, that's funny because this exam, when we gave this exam, they hadn't gotten to chapter 7 either. So we told them it's an SN2 reaction. They just didn't know that. Okay, so the following one-step reaction proceeds by nucleophilic attack of the bromide, loss of leaving group. Okay, so they were given these molecules and they drew the arrows to get these products. Okay, so they went from having a alkyl chloride to having an alkyl bromide. So they were asked which of these two mass specs support the formation of the product, the alkyl bromide. So the two peaks that are important are M and M+2. So this one is M+2, but they're in a 3-to-1 ratio. M and M+2 here are in an almost 1-to-1 ratio, and that is the isotope distribution for a bromine. That's how you know it's a bromide, because of the 1-to-1, almost 1-to-1 ratio in M to M+2.
Okay, thanks.
Yep.
Can you go over number 10?
Yes.
Cool.
Okay. Consider the proton transfer reaction shown below, which statement is true. Okay, so we have a sulfur-based acid, propionate, deprotonated. Okay, all right, so I'm just going to write some things on here that I would need in order to analyze this question. Whether you guys did that or not, I just need to see some notes. Okay, so this is the conjugate base, conjugate acid. Okay. All right, so the other thing we're going to have to deal with is areo. So atom identity or carrying charge. Okay. So this is a proton transfer reaction. And what we're going to have to compare is essentially base stability. Okay. So we have two bases. We have an oxygen base and we have a sulfur base. So the atom for carrying the charge, we have to remember that sulfur and oxygen are in the same group. Okay. Bigger atoms like sulfur stabilize charge better than smaller atoms like oxygen. Okay. Are you with me so far?
Yeah.
Okay. So since the bigger atom is sulfur, and they both have resonance, but this is going to be oxygen carbon to oxygen, sulfur carbon to sulfur. So they're going to have the same or similar resonance stability. So it's really, I think, going to come down to the size. So this can stabilize the charge better. So this, comparing the bases, this is the weaker base, stronger base, stronger acid, weaker acid. Okay, so the direction of equilibrium will always go from the stronger acid to the weaker acid. So we could, even though you don't have the pKa values, you always go from strong acid to weak acid. So this is right-hand side favored. And B says to the left, C says to the left, D says they'll be equal. That's pretty unlikely. So A is to the right. So as long as you know, based on acid-base stability, that if you can work through that analysis using atom identity and then ranking strength, then you can show the direction from strong acid to weak acid. And then the reason it's true, because sulfur is better able to stabilize a negative charge. So you could have stopped just right down here. But I kind of like to have two pieces of information that tell me the same thing. Do you see what I'm saying? Like, once you know that the sulfur is able to stabilize a negative charge, that's great. But then does that correlate then to the direction of the arrow based on ranking relative strength?
So low pKa to high pKa.
Yes,
And-
low pKa to high pKa.
And K is inverse, like K equilibrium.
Yeah, so if you write out your equilibrium constant, so the equilibrium constant K is some number greater than 1 or less than 1. pKa is equal to the inverse log of Ka. If Ka is big, pKa is small, and small, pretty much negative. Negative, yeah. So if K is greater than 1, and that's very big, because things like strong acids will have K values of like 10, 15, 20,000, like huge numbers. So then the pKa is negative. Then the reaction,
Favored?
say that again?
Is that reactant favored?
No, it's product favored. So for example, if you took the acid dissociation of HBr, okay, we could say HBr will make a proton plus a bromide. Okay. Now you know from the 7 strong acids that HBr is a strong acid. So it fully moves to the right. So this is a product favored. So K is much greater than 1, pKa is less than 0. Then you could go even farther and say, then the delta G is also negative. So the reaction is spontaneous to products. But that's just acid dissociation. This is essentially comparing relative strength when you have multiple. I mean, you could do this with water and do the same sort of analysis, but with strong acids, if you remember the 7 strong acids and you know their product favored, then K is huge, pKa is negative, delta G is negative.
Okay.
I have a question related to the bases and the acids,
Okay,
and the ranking.
okay.
If they are, if we're questioning the stability of 2 different bases, and the 2 things are not in the same group or the same period, can you?
You
Like-
wouldn't be asked that.
Okay, okay, cool.
Yeah, it would be very difficult right now for you to take like an oxygen carrying charge and compare it to like a phosphorus
Okay, cool.
charge. Yeah, so I mean, you can't, you gotta walk before you run. It's more, you know what I mean? Like, just remembering in a period it's electronegativity and in a group it's size, right now that's enough.
Okay, great. That sounds like plenty to me.
Yeah, I agree. Okay, Carter's question, will you go over how to distinguish between Bronsted-Lowry acids and Lewis acids? Sure. That is going to be with respect to what is, whether or not a proton is involved. So all Bronsted-Lowry acid-base reactions involve proton transfer. Okay. So the acids are proton donors, the bases proton acceptors. So we could write HCl plus H2O to give you H3O plus chloride. Okay. So this thing was the acid, and this was the base. All Lewis acid and base reactions involve electron pair. And the acids are electron pair acceptors. And the Lewis bases are electron pair donors. Okay. But you can describe this Bronsted-Lowry reaction by the Lewis acid and base model by saying that what happens is, this is again the base, it's going to donate a pair of electrons to the empty orbital in the hydrogen, and the chloride will break off. Okay. So all Bronsted-Lowry acid-base reactions are Lewis acid and base reactions. Okay, but you can have Lewis acid and base reactions that don't involve the transfer of protons, just the transfer of electron density. Like that. So all Lewis acids and base reactions, all Bronsted-Lowry reactions are Lewis acid-base reactions, but not all Lewis acid and base reactions are Bronsted-Lowry reactions. There's no proton transferred in this reaction, but it's still a Lewis acid and base reaction.
Would we be given the products and reactants, or would we have to figure out the products?
The only way you would have to think, of what kind of reaction?
For like the Lewis, like identifying like a Lewis acid base or something.
No, not quite at product prediction yet, unless you're told the steps. So like now you guys know about substitution. But like if you remember back from that last question that Ursula had asked about, where you were told to draw the products when, and then you were told the patterns of reactivity. When nucleophilic attack, and that's one of your chapter 6 patterns of reactivity, and loss of leaving group occur in one step. Okay, so with knowing that one-step reactions have to include a collision between the two species, and then told what kind of steps are happening, you should be able to predict the product. But for tonight or this afternoon's exam, without that, no, you're not responsible for knowing the product of that reaction. Next week, Monday, yes, you are. So chapter 6 had, it has the patterns of reactivity that you're going to see in all the reactions we do for the next 2 weeks. But they're presented as like named steps. And so you should be able to monitor electron flow. You should be able to name the steps if you're shown the arrows. But product prediction we're not quite there yet.
Can you go over the like constitutional isomers and enantiomers and stuff?
Sure. So in your isomers, they get split into essentially different connections between atoms. And same connection between atoms. So for different connections between atoms, you would have the same formula. So like C3H8O. And you would get 2 alcohols and then an ether. Okay, so these are connected differently. So this is a primary alcohol, secondary alcohol, and then this is an ether. Okay. Same connection between atoms. But they would be non-superimposable. if they're non-superimposable, but they're mirror images, they're enantiomers. And they would be opposite at all chiral centers. That's my mirror plane. Okay. If they're not superimposable, but they're not mirror images, then they're diastereomers. Okay. And then those would be, if you had a compound RRR, then you would have one enantiomer, which would be SSS, and then it would just be some or different, oops, you can't see what I wrote. Some would be opposite, but some would still be the same. And the enantiomers are going to have the same physical properties. They'll have the same intermolecular forces, the same polarity, same melting point, same boiling point, same water solubility, equal but opposite optical rotation. A diastereomer will have a different melting point, a different boiling point, and a different optical rotation.
If you have a compound that's has like, say, bromine and chlorine, but like on a dash and a wedge, how would you rotate that to find the rotation, like the stereochemistry for that?
But bromine has a higher atomic number than chlorine, so you'd be able to rank them.
Okay, so it's just whichever one is higher you would put on the wedge?
Well, no. You'd have to look at the compound. So one of the things, and I think this is something that you do in lab, I could be wrong, but like the activity will say, draw S2 pentanol. Okay, so what I would do is I would say, okay, I'm going to start here with pent. That means 5. Okay. Then I would decide whether I wanted to number from right to left or left to right. So I'll start over here this time. I don't know by looking at this template whether or not the hydroxide has to be on a dash or a wedge. But the easier place to start is to do the hydrogen on the dash. I don't know if this is right or not yet. This is one enantiomer. I just don't know which one. Then I would do my ranking. And it just so happened that I drew the S enantiomer first. But I personally cannot read that and automatically draw this and know that it's right. So if you're asked to draw an enantiomer, your first assignment of dash and wedge is a guess. Then you check it by doing the priority. And if you're wrong, then you draw the other enantiomer. So if this had been draw R2 pentanol, and I did this, and I figured out that I was wrong, because I just put an assignment on there and it happened to be F, then to make R, all I would have to do is switch those 2 positions, and I don't even have to redo the assignment. Now this is R, because I made a change at 2 bonds. So I think the way that and I could be wrong with it being a lab issue, but if memory serves correctly, this is something that happens, is if you have a name with stereochemistry and you're asked to draw it, the skill is not in drawing it perfectly correct the first time. The skill is in drawing a structure analyzing the chirality, and then determining whether or not what you've drawn answers the question. If it does, you're finished. If it doesn't, you draw the other enantiomer, and then you're done. Does that make sense, Ben?
Yes.
Okay, good. Okay, well, if there aren't any more questions, we will be done. I will be,
Dr. Walters,
yes,
just one more quick one.
sure.
So it says on the study guide, we need to be able to determine the number of stereoisomers by the number of chiral centers, and that's
Yes.
fine. That's, you know, that 2 to the n thing.
Yeah,
Now, it also asks, it says we need to know what effect, you know, a plane of symmetry, so like a meso compound would have on that. I know
yes.
that it reduces the number of stereoisomers. I
Uh-huh.
don't really know by like what, do we need to know by like what factor?
No, because it's
Okay.
going to depend on how many chiral centers you have. So the
Yeah.
easiest example is if you have 2 chiral centers and an interior plane, then you're going to end up with 3 stereoisomers. It's
You'll
almost
have the
more,
enantiomers in a meso.
yeah, a pair of enantiomers and then a diastereomer that is meso. It's so the things with meso is if you see a structure, you should be able to identify if it is meso. If you can look at a molecule and say that molecule has a mirror plane, so the chirality is negated. So you should be able to identify a meso compound and then rationalize that it would have no optical activity, even though the diastereomers of it that happen to be enantiomers would have optical activity.
Yeah, that's fine.
Okay.
All right, thank you.
Yep. Yes, the test is going to open at 4, just like the last one. Everything is essentially the same protocol. So 25 questions. The periodic table will be available. We have 1 attempt, hour and a half. It should be exactly the same as last time in terms of how it works. Okay, well, if there aren't, yes, you can. You can use your own. So, and yeah, scratch paper, yes, don't feel like you can't write. So my understanding with the way the program works is if the program thinks that you're not doing what you're supposed to be doing, I don't think it kicks you out unless you try to open up another web browser. I think it just flags your recording, and then I get sent the recording and have to watch it. So you should feel like you can draw and stuff like you normally would.
So would we just like hold up our scrap pieces?
Yeah, I think it asks you to hold up your scratch paper. It needs to see your face, the webcam, you know, your pencils and stuff like that. But I don't think it's like a kick out unless you try to open a browser. If you try to go outside the browser, I'm sure it kicks you out. Okay, guys, so we will, there's gonna be no rest for the weary for the next 2 weeks. So the reactions really kick in. We've started a little bit with 7, but pretty much everything towards the end now is reactions. So good luck tonight or this afternoon. Let me know if there's any issues, and we'll be in good shape, okay?
Thank you.
All right. Yeah, you're welcome. Have a good day. It looks humid but pretty out. I'll talk to y'all soon. Yeah, you're welcome. See you tomorrow.